Hello everyone, I think we can start today's colloquium. So we have the great pleasure to welcome Professor François Delarue from Université Côte d'Azur. So just a few words about François Delarue. So he studied at École Normale Supérieure de Lyon and obtained his PhD in applied mathematics at the University de Provence-Marseille in 2002, supervised by Etienne Pardou. He works on stochastic processes, probability, and PDEs and midfield games from both theoretical and numerical points of view. He is the initiator, together with René Carmona, of the probabilistic approach to midfield games and the author of the widely read book Probabilistic Theory of Midfield Games with Applications. He has been a member of the Institut Universitaire de France between 2014 and 2019. And in 2020, he obtained the AMS Duke Prize and the SMF SMILE Prix Maurice Audin. So thank you very much for coming.
Thank you.
So the floor is yours.
Thank you. Thank you for the kind invitation and thank you for the very kind introduction. So indeed, I'm going to speak about one of my favorite subjects, which is midfield games. So I will try to give you an overview of what it means and what you have behind. So I will start with very basic things because I know that some of you are completely away from the field. So I will try to give you first the basic idea, what is the general philosophy of those midfield games. So this is something that was existing before mathematics, let's say in economics. You can find some of these models. And the very basic idea is to say that you have games. I'm going to explain to you what it means, even though myself, I am not a specialist of game theory, but it means that basically you have many people. So you see that this is really crowded and you have all these people. And in fact, these people, they want to minimize for their own some costs, some energy. I will give you some examples next. And the very key point is that they are selfish, so that they just want to act for themselves. So that's the first point. But on the other hand, there are some interactions between these people, and so they are competing. There is a competition, and what you would like to do is to find a compromise between these people. So, what would be the definition of a compromise? I will give a mathematical definition of this next, but there is a famous guy who worked in this direction. His name is Nash. It's not the same Nash. I checked with the organizer. This is not the same Nash as the one you have here. Basically, it means that if people are in consensus or in compromise, they don't want to leave, or they have no interest, no incentive to leave the compromise. So this is a kind of equilibrium that we are looking for next. Another feature of the model that I'm going to look at is that they evolve with time, which makes the model more difficult, and you will see some dynamics appearing next. Now you say, well, there are many people. So certainly if you want to try to characterize mathematically what are those compromises, then you realize that this is really complex. And specifically, it might be even more complex if the interaction that you have between the individuals are also very complex. So you can make some simpler assumptions on the type of interaction that you have between the individuals. And this is the key point in this notion of mean field. So the mean field means, so this keyword that you have here, it means that you have a kind of specific type of interactions between the individuals, which covers, in fact, a quite broad types of models. And what it says that people see one each other through some aggregate quantity. So think of people who are consuming, somehow they share a common quantity which is the price. So let's say the price of electricity, the price of oil, for instance. And mathematically, what is the price, or what is those aggregate quantities? Well, these are quantities that depend on the collective state of the population. And this is exactly the picture that you have on the top of this slide. So you take one individual in the population, and this individual sees the others through the collective state of the population. So if if you know a bit of statistics. So clearly you recognize a histogram. This histogram is just here. This is just a picture to say that what you see is the collective state of the others. So you do not know exactly who is who. You just see the crowd of people in the room. So I don't say exactly that Roxana is over there. I just see here the people collectively distributed in the room. So this is exactly what happens. And then you realize that if you do this kind of assumption, and if you assume that there are many people, certainly you are saying that as the number of individuals in this game is growing, certainly one individual has a lower and lower influence on the others. This is exactly what I'm saying here. When you grow up the number of people in the population, then certainly one agent has a nearly infinitesimal impact on the rest of the population. And so its possible changes, so the way it's going to choose the way it behaves to minimize your energy or to minimize your cost, certainly this is going to have a very small influence on the whole state of the population. And when you say that and you are a probabilist, then certainly it tells you that possibly you should have a look at games with a continuum of players, a continuum of particles. And this is really the starting point of this theory of mean-field games. You pass to the limit in a mathematical manner, and you directly solve a game where this population is replaced by an infinite cloud of players. And then you say that possibly this might be easier to solve due to the type of interactions that you have assumed between these individuals. So this is exactly the program that you have in the theory. And even though the theory was started in the mathematical area something as 15 years ago, you will see that some people already thought about it in some way. I will give you some sentence next. So you can have a look at these works by Oman in macroeconomics. So once again, the idea is to say that when you let the number of particles tend to infinity, certainly there will be some statistical phenomena, which are very well known from people from statistical mechanics, which is to say that there will be some decorrelation between the individuals. And when you have a look at the collective state of the population, maybe you are going to see some theoretical distribution instead of some empirical distribution for those of you who know statistics. And once again, the guess is that thanks to these verging phenomena, you may solve problems with a lower complexity. And from a practical point of view, for sure, this has an interest because this should be or this could be easier to solve. And just to go in this sense, this is a copy of a sentence that you can read in the book of von Neumann and Morgenstern. So this was a book that was written after the Second World War on game theory. And this is a very nice sentence. And this is exactly what they claim. They claim, well, in fact, if you have a look at systems with a great numbers of particles, individuals, this might be easier to handle, which is exactly what you have here, because of the laws of statistics and probabilities. And this is exactly what we are going to see next. Since the population is really large and you have this kind of weak interaction between the particles, there are some verging phenomena because of which the equilibria, the compromises are easier to find. So this is the guess of the talk. So you mix two things. You mix game theory, which is related also to optimization theory, and you mix some tools from statistical physics or probability theory. And this is the reason why I guess this subject has become popular for 15 years. The reason is that this is at the interface between different fields from mathematics, so probability and statistics, and optimization. And you will see that there is also PD in the talk. So I think that this is one of the reasons why it has become popular, beyond the fact that it has some application, as these pictures can show up. So let me just say that these are 4 possible applications of the theory, some examples that you can find in the literature. And let's say this is just a way for me to cite one of the father of the theory. I will give you more references about that next. but in France. And this is one of the reasons why several people, many people in France started to look at this theory. One of the fathers is Pierre-Louis Lyons. And this is, in fact, for those of you who know Paris, this is the roundabout Place de l'Étoile. So this is a huge roundabout. And you have all the cars. So this is in France, so we are running in this direction. And you see that all the individuals now, they are drivers. And what you want to do is if you enter from one way the roundabout, somehow you want to exit as fast as possible from the roundabout. So, well, you want to minimize the total energy that you are spending plus the time you are spending inside the roundabout. But for sure, you are seeing the others, and you really see this phenomena of aggregated quantity. You don't really care that this is who is driving this car. You don't care who is driving this car. What you care is the local density of vehicles that you have around you. If there is no vehicle, then clearly you can run fast and you can cross quite fast the roundabout. Now, if there are plenty of vehicles around you, for sure, so the density is high and it takes you more time to exit the roundabout. So this is clearly a competition game with many particles. This is exactly the same phenomenon for this picture. Assume that you have, I don't know, fire that starts in the whole of this airport and that everybody wants to leave as fast as possible. Clearly, what you want to do if you are one of these individuals is to reach the exit doors as fast as possible. But then you will meet the others and you will meet the local density of the other people in the story. This is another example, and I guess that Roxana is a much better expert of this kind of examples than myself. This is to say that people use mean field game theory in, let's say, generally speaking, in math finance here. This is for electricity markets. So you have people that are consumers of electricity, but also producers of electricity. So if you're at home, you consume electricity, but at the same time, if you have sun, then you produce electricity with those solar panels. And then there are not only global producers of electricity, but also local producers. And those local producers are also local consumers. And at the end of the day, you have the price of electricity, depending on the consumption of all these people. And so all these people, they meet this common information and they see one each other through the price of electricity. And you have people working on these electricity markets, and also working in like in France, maybe this is the same here in UK, for big companies producing electricity, and trying to see how to incentivize people to consume electricity at a time that is good for the society. So instead of consuming exactly between 6 p.m. and I don't know, 9 p.m., which is the peak of consumption of electricity when everybody comes back home and tune on the heat, if this is called outside, trying to smooth out the consumption of electricity. So these are really real questions that I'm sure about this. People in electricity companies, they work on these kind of problems. Here, this is a more prospective remark that I'm not able really to address next. I'm just going to say one line at the end of my talk if I have time enough. This is just to say that people also use the tools from mean field games or related mean field optimization. I'm going to say a word about this in connection with machine learning. I'm going to say next a few words about this, but this is a more prospective direction. Okay, so this was a kind of generic introduction without any equation, any mathematical symbol. So now let's try to see how you can put maths. And so you have to put a model for this, trying to put some dynamics and trying to model the interaction between people. So in terms of mathematics, you have several features, or maybe some of you know these keywords. The very first thing is that I'm going to assume so that I have particles, and those particles have the following features. The first one, they will evolve with time, so you have some dynamical systems, and they are controlled. So you can tune some parameters inside the dynamics so that you want to minimize, or in order to minimize a given cost or a given energy. So typically, if you think of a particle, you can tune the velocity. I'm going to come back next to this example, but this will be the benchmark example I have next. And I'm a probabilistic, so I will put some noise in the dynamics of each individual. These are some shocks that I'm going to meet when I'm moving. So this is for one typical individual. So I will give you next the precise dynamics for this, but these are the keywords that you are going to meet next. Mean field, this is what I said. This is the fact that, well, the interactions are through the collective states. And so there is a kind of symmetry in the interaction, and plus the fact that when the number of particles tends to infinity, my influence on the rest of the population gets smaller and smaller, which is absolutely a crucial point. And for those of you who know a theory of interacting particle system, this is typically what we call weak interaction or weak interacting particle system. Now, these are individuals. They see one each other, and each of them is assigned a cost functional or an energy functional, and everybody is willing to minimize, everyone is willing to minimize or wants to minimize her cost or her energy. And then you have this notion of Nash equilibrium that I spoke about. There is no interest for you to leave the consensus. What are the key questions that you can have in the literature? So once again, I will give you some references next. Can you find compromises? So this is a basic question that you have in game theory. Is it possible to prove that there are some equilibria? So usually this is the very first question. What about uniqueness? Which is a very much more difficult question, and we have fewer results about uniqueness, but you can guess that for stability reasons, for numerical reasons, for learning reasons, this is very useful to have some uniqueness property. What about the shape of the equilibria? A very interesting question, at least for myself. I think if there is no uniqueness, is there any way to select some equilibria instead of the others? I will try to give you some example next. Another question, which is absolutely fascinating from a mathematical point of view, once you have solved the game with an infinite number of players, are you able to make a clear connection with the game with a finite number of connections? So these are convergence results. So you can guess that this is connected with large behavior of particle system. And next, you can find plenty of other questions, numerical methods. You know what is the model, or learning. You don't know the model, you have the data, and you have more and more people in the ML or RL community that try to do these things. Some references, this is absolutely not exhaustive. Here you have the fathers of the theory. So I told you about Lyons and his co-author Jean-Michel Lasry. And so for those of you who are interested, there is a very nice series of video from the lectures of Lyons at the Collège de France. So this is online. And also these people who did a lot in Canada from engineering. So more or less at the same period, they gave many applications of mean field game theory to communication system, for instance. Then there are several branches of directions of the subject. So people who study the theory by means of PD, and I will try to explain to you next how you get PDs in this story. So these are some names, but this is not an exhaustive list. Here on the probabilistic side, once again, a few names. And recently, those people who did a lot for learning, and I know that some of you are interested with learning, and really they did a lot, and what they did is really nice. So, now really a question. So I'm entering a more mathematical part of my talk. So from a probabilistic point of view, this is what we call a stochastic process. So this is one typical evolution for one individual in the population. So now I have to put a model on my problem. So here you see that I have an index I. I'm studying for the moment just the system with a finite number of particles. I'm trying to derive step by step what should be the mean field game. So I'm restarting from the original model when the number is finite. So I is just running from 1 to n, and I have somebody who evolves from the initial time 0 to a fixed capital time t, which is the finite horizon. And here this is her velocity, and her velocity can be tuned So this is a parameter in RD that I can tune at any time. And here, this is the infinitesimal increment of a Brownian motion. So for those of you who do not really know what is a Brownian motion, it means that at any time t, somehow I'm flipping a coin to decide in which direction I'm going, if I am working on the real line, or if I am in more generally in the d-dimensional space. I could flip a coin to see, I could flip a die if I would be in a given dimension, or more general random trials to see in which direction I'm going along the grid. And here, this is the limit of this kind of model, meaning that this is a Gaussian increment, in fact. So this is the continuous random walk, meaning that this is a Gaussian increment. And in the Brownian motion, this Gaussian increment is independent of the past. So this is independent of the past, and the variance of this increment is dt. So the variance is proportional, and in my model, this is exactly equal to the time step that you have here. So this is dt. The noises are independent, so I assume that the players, they have their own shocks, and those shocks are independent. And the very key point is that the way I choose my velocity cannot anticipate on the future of those Brownian motions. So this is something that is absolutely classical in stochastic processes theory. So I am taking my decision based on the observation that I have up to a given time. You can have random initial conditions, and then they're assumed to be typically IID, so independence with the same distribution, the same statistical distribution, and independent noise. So this is a bit theoretical mathematical framework or probabilistic framework. You can more or less forget it for the rest of the talk, except for one fact, the independence. And I will come back to this notion next, and there is a basic result from probability theory that I need, and I'm sure that all of you know about this result. So these are the motions. So you have to think of tuning my velocity, and I am receiving some shocks along the motion, and those shocks, there are independent Gaussian increments. Everybody is receiving a cost. So Ji is the cost to the particle number I. The very key point is that this cost depends on the velocities of the others. So this really creates the interaction between the particles. And this is a cost. So this is a mean cost. So here, this is the symbol expectation in probability theory. It says that I take the mean over all the possible scenarios for the shocks. Okay. And so this is an average shock. And the price that I'm going to pay, I'm going to give you an example for this, or almost an example for this, but this is typical of what you have in stochastic control theory or control theory. So you split up the cost in three parts. So here, this is a kind of, I'm sorry, I'm missing the dt for this time interval. So this is a typo, dt is missing. So here, this is the square of your velocity. So this is a kind of kinetic energy that you would like to minimize along your path. Here, this is a potential energy. You are xit, so this is your location in the space at time t, and you see the others, and the others, they are summarized through this object in blue. I'm going to come back to this point at the bottom of my slide. And so this is along the path, so you have some potential cost for the interaction of the others. And then possibly you can put a terminal cost just to see how at the end of time you see the others. Let me give you an example for this, but before I do that, let me explain what is this blue term. This blue term, this is what we call in probability theory, the empirical measure of the system. This is the key fact. So you want to describe the collective state of the particles by a probability measure. And the probability measure is obtained in a very simple way. You put a Dirac mass or delta mass at any points of your clouds, and every delta mass is receiving 1/n as weight, and you make the sum. Okay, so basically this is, if you plot the histogram of your state of the population, this histogram corresponds exactly to the description of this probability measure. So this is an object that is very well known in statistics. So this is a way to describe the state of the population. Let me give you an example just for this function, this potential of this interaction function. So Typically, I can assume that G takes values or is defined on RD. So RD is the state space for the particles. And you see that I compute if G is a potential function, so I compute somehow the potential for the interaction between Xi and Xj, and then I make the average. This is a typical example that you can have in practice. Okay, so far so good. Everybody is receiving this cost, and now you want to minimize your energy, but everybody wants to minimize. So at the end of the day, there should be a compromise.
Where do we see the empirical measurement?
Well, here you say that this is a convolution, meaning that this is G of Xi minus little x. Yeah, here, absolutely. And here I can do the same by saying that it can be written as a convolution of G with respect to the empirical measure, okay? So once again, you say that this sum over the j's, this is exactly an integral with respect to the empirical measure. So this is the convolution of G with respect to the empirical measure computed at point Xi.
So in the general formulation, the function does not need to be an integral with respect to the empirical. It's just any function.
No, this is any function. Absolutely. Here, this was an example just to show you what is the typical choice. Absolutely. So what is a compromise? So a compromise is exactly what I told you. This is a situation from which nobody has an interest or from which I should not leave. So this is exactly the definition. So just to denote a compromise, usually I'm using this star notation. So when you see this notation star, it means that this is a compromise or an optimizer of something. So this is something that is very good for my optimization problem. And so once again, this star tuple. So you have to see that all these things, they depend on time, because at any time I'm choosing one motion. And so there is no interest for a given player to leave the consensus or to do the compromise. This is exactly the definition of a Nash. So it means basically that if you take your collection of tuples alpha I star, and if you take one guy I, and you assume that the guy is ready to change for a new control, a new alpha I, then the cost, his cost or her cost is going to increase, which is exactly what you see here. The others are freezing their control, and the cost is increasing. So here, this is below than this one. So there is no interest for me to leave the consensus or to do the compromise. Now there are some subtleties in what you mean by freezing the orders. So you can regard these controls as a function of the noises, or you can regard those controls as function of the locations, of the position of the individuals. So here in game theory, control theory, this is what we call control in closed loop Markov form. It means that when you take your decision to decide of your velocity, you just observe where the others are, and then you take your decision. You don't have a look at the past of the past of the system. When n is fixed, the equilibria are not the same depending on the way you freeze. When n is equal to infinity, this is the same. Okay, so I don't really care about this subtlety for the rest of my talk, so you can forget it. But for those of you who know the difference, there is a difference. Okay, how should I do that now? I would like to let n tend to infinity. So I would like to see what is this problem when n tends to infinity. What is the guess? The guess is that when I take my decision at the compromise, I should keep track of the mean field form of the system, which is to say that I should certainly have some compromises for which my decision is at time t is of this shape. I decide in terms of my own position and the position of the rest of the population. So I should be able to have some policy or some strategies or some controls that only depend on my own state and the state of the others. The difficulty is that this function that depends on the states of my own state and the rest of the population, this function depends on n. Let me make the following assumption for the moment that it does not depend on n. So this is just a given array. This is a great simplification. And in fact, this is a real spice of the problem. It means that for any of the particle now at the equilibrium, I should replace alpha n by alpha n red. And now this alpha is independent of n. And for those of you who know statistical physics, this is what we call an interacting particle system with weak interaction. And we have plenty of results for this. We have results from probability theory since the work of McKean in the 70s. And we know how this system behaves when n tends to infinity. There is a result that is called propagation of chaos that says that when n tends to infinity, the particles they become independent. So here you see that when I am player I do depend on the noises of the others. But when n increases, I feel less and less the noises of the other players. And so asymptotically, the particles decorrelate, and since they become independent, and you see that there is a kind of symmetry, statistical symmetry, or we say that they have the same statistical law here, certainly this empirical measure by the law of large number, it should average, and it should look like a theoretical distribution. This is the guess. This object is random when n is fixed, but when n tends to infinity, it should converge to something that is deterministic. It should converge to the theoretical distribution of the population. So this is probability theory. This is the law of large number. And it says that when n you pass to the infinity, you should have a look at only one particle in the system. Instead of having a look at the whole cloud of particles, you just summarize the dynamics of the system, but by one typical guy. So let's say x, and the velocity of this x is just driven by its own theoretical distribution. So L of xt, this is for the law of x. And so you see that you have simplified the problem. Here you have a cloud of particles. Here you just have one particle. Here the interaction are with the others. And now you just say that this given particle is just interacting with its own distribution, which is, okay, this is a reduction in the sense that I only have one type particle in the system. And now I say this mu bar n should look like this law of xt. I'm going to call it mu t. It says that when n tends to infinity, certainly in the limiting compromise, the interactions, the argument for the interaction should be a deterministic quantity. It's no longer random. So what I'm going to say now, I'm going to say, I want to have an intrinsic description of what is this mu t, okay, which is exactly what I'm saying here. So I would like to describe what is mu, and mu will be or should be the statistical state of the compromise. And this is exactly what you track in the theory of mean-field games. So now this is a formulation of the mean-field game in the mathematical manner. So you are looking for a candidate for being the statistical state of the compromise. So this is a collection of probability measure, and at each time t, this is the state of the population at this time. And you say, how should I do that for characterizing this mu t? I take one typical individual in the population. It evolves according to this equation. This is the velocity that might be tuned or that can be tuned. And this is the noise, that is a Brownian motion. And this guy has a cost. And the cost is exactly this functional. But now you see that this is simpler. In the interaction, I have replaced the others by my candidate mu t. And I say, this mu t now is a kind of environment. And what the guy is willing to do wants to do is to minimize the cost given the state of the population. So I am minimizing, so I am solving this optimization problem. This is no longer a game at this stage. This is a minimization problem given the state of the population. And the third step is to say, I remember of the Nash condition. The best response should be the environment itself, which is to say that to have an equilibrium, to have a compromise, I should say that the law of my best response, or the law of the optimizer, this should be the law, or this should be the candidate, the equilibrium itself. Yes? I'm sorry?
Why do you have a quadratic?
No, you could put a more general Lagrangian term, but here this was just for the talk to simplify. You can have a more general Lagrangian. if this is convex, basically with nice growth properties, there is no big differences. If this is included in the function f, this might be more difficult, but you have a series of results depending on the shape of your Lagrangian. Here, this is just alpha squared because this is simpler at the end of the day to minimize with the quadratic. This is much simpler. This is to simplify my talk. So this is the definition of an equilibrium. You are given a candidate, you solve for one attack particle in this environment, and then you identify the law of the best response with the environment itself. So now you want to track those fixed points. A Nash is a fixed point, and you want to get your fixed points. And for sure, you would like to characterize those fixed points.
So this was still consistent to the new E on the left-hand side as an argument.
No, this is a non-trivial. Yeah, absolutely. No, this is a non-trivial. Now you want to solve this fixed point, and the very first step is to say whether this is possible indeed to have some solution to this problem. I'm not claiming that this is easy. I'm just saying that this is what you have to solve to get some equilibrium. And this is not a proof of convergence. This is just a way to say when n is equal to infinity, this should be my problem. Oh, indeed. Another formulation of this fixed point problem, for those of you who come from the PDE theory. One PDE theory said that there is a nice way to characterize the minimizers in this step, and now you will see the reason why I have chosen this alpha square. This is a standard stochastic control problem, and in PDE theory, this is exactly the same as solving a Hamilton-Jacobi equation. So I will get, for this minimization problem, I will get a Hamilton-Jacobi equation, which is exactly what I'm saying here. How do you do that in control theory? You say that you provide an Eulerian description of the problem, so you freeze the initial time and the initial state of the private player, of a given player, and you say, now it starts from little x at time t, and I am minimizing this quantity when the environment u is fixed. U is what we call the value function, and we have a description of this u. This is stochastic control theory. It solves a PDE. So this is a second order PDE, second order because you have the Brunner motion. From a PDE point of view, you get the Laplace. And here you have exactly the Hamiltonian. And you see that the shape of the Hamiltonian is really simple because you assume the Lagrangian to be quadratic. And so you have that you just have to minimize with respect to alpha this quantity. Well, this is pretty easy. And you get this equation, which is one of the standard equations you can have for the HAP equation. You can have a more difficult equation with a more general Hamiltonian, but this is absolutely useless for my talk. So when mu is fixed, you have to solve this equation, but you see that this equation depends on mu. And now you want to track mu. How to get mu? You say, once I have solved this HAP equation, I know what is the optimal policy, the optimal control. This is something that we know. The optimal control is exactly given by minus the derivative of u. It comes back to this computation. In fact, you have a look at the best alpha, and then the best alpha is exactly given by minus the derivative of the value function. And so this is the equilibrium trajectory. When the law is given, u depends on mu, and so the trajectories that you have here depends on mu. But now you recall one fact, which is the fact that the law of this guy should be mu itself. This is this non-trivial condition that you were mentioning. And in PDE theory, there is a very, very easy way to describe the evolution of the law of a stochastic process of this type. And this is what people call a Fokker-Planck equation. People from physics, they know this. So you describe the evolution of the law of this guy in terms of this PDE. And you say, but the law of this should be mu itself. This is my consistency condition. And so at the end of the day, I have to solve a forward equation for the evolution of the population. But the drift here, it depends on the solution to this backward equation. And so this is a coupled system. But the difficulty is that the coupled system runs in opposite direction of time. There is one equation that is forward for the evolution of the population. And here this is a backward equation because the boundary condition is given in terms of the terminal cost. And so you have conflicting directions of time. And because of that, this is non-trivial. If you want, this is the infinite dimensional analog of a two-point boundary problem. You have an ordinary differential equation x dot in the forward direction. The drift or the velocity would depend on a component y that would be running in the opposite direction. Yeah.
This delta
This is the Laplace operator. So this, yeah, for the measure. So two things. Either you said that the equation is posed in the weak sense, fine. So you make integration by parts, or you say that in fact, because of the presence of the heat operator, even though you start from a measure, you will get some density, positive density after some time, and even smooth density. And so this will have a classical solution, certainly. For sure, it might depend on the smoothness of this drift, but at the end of the day, you can prove that indeed you can have really smooth probability measures. And so this is not only a distribution, this is a function. Okay. You can solve this. Not that easy, but existence can be proven by compactness arguments. So we have some existence without uniqueness, so Schauder type results by using some smoothing properties of the heat operator, or this is the way you get some existence results. Uniqueness is a more difficult result. I should say a few words about uniqueness, and you will see next why this is important. When you have a forward-backward system, this is difficult to solve. And in fact, if you know PDE theory, you know this for some conservation laws. If you have a look at the characteristics of some conservation laws, you may represent the characteristic in these two opposite ways, and precisely the fact that the two directions go in opposite way, the two directions run one backward and one forward, this creates some difficulties. Take one very basic example for this phenomenon. You take the Burger's equation. Okay, you will see what is the generalization of this Burger's equation for mean-field games next. So this equation here, this is in dimension 1. So this is just this equation. So you see that the velocity field is exactly the solution of the equation. If you think of characteristics, it means basically that you have that the velocity is y or minus y, and so you have that your motion is along minus y is v of x, okay? And so y dot, this should be the derivative of this. But when you compute the derivative of this and you plug the PD inside, you get that y dot has to be 0. And if you freeze the boundary condition now, which is exactly the boundary condition of the PD, exactly as we have in our problem, then you realize that indeed you have a forward-backward system in dimension 1, okay, in finite time. And now you see that you have plenty of phenomena from the qualitative point of view. If you take this boundary condition that is non-decreasing, this is a plot of the characteristics. So this is a plot of these, of the trajectories for x, depending on the location of the initial condition. Everything is fine. I have uniqueness of the characteristics. Now, if you change the shape of the boundary condition, if you reverse, you take the opposite, then there is a conflict at the initial time. There is plenty of characteristics. You completely use uniqueness. This is a shock in hyperbolic equation. And you have exactly the same phenomenon for mean-field games. I'll try to convince you next if I have time enough. So clearly, to have uniqueness in this kind of problem, you need you can use some monotonicity condition. Okay. And now, what is monotonicity condition for mean-field games? So this is something that is really famous, and this is a condition that is due to Lasry and Lions in their initial papers. You require f and g to be monotone in the direction of the measure. So you see that you take f at mu prime, you integrate with respect to the difference mu minus mu prime, and you require the integral to be non-negative, and the same for g. If you have these two conditions, then there is uniqueness, a unique equilibrium. Okay, so this is the typical condition that people use for uniqueness. There are some extensions, but this is not that trivial. Because if you think in terms of characteristic, they can be you can have shocks. Yeah, you have some intuition. So this is a typical example that I can give you. It says that basically the examples that you have are examples in which people don't want to be together. They want to be spread out in the space. So in this example, we can discuss more about this example, whatever the formula. It says that if I have no incentive to go to places where there is an accumulation of mass. So at the end of the day, you want the mass to be spread out on the space. This is exactly the intuition that you have in the example.
It's like the gradient descent.
Yeah, so gradient descent in the sense, well, this is connected with gradients in the sense that if you think as f as a derivative with respect to a measure, it means that the function that is above is convex with respect to the direction of the measure. Maybe yeah, exactly. So this is exactly. So once again, if you think of f, it might not be a gradient, but if this is a gradient, it means that the potential is convex. Absolutely. Absolutely, absolutely. I do agree with this. Okay. You tell me when I have to stop. But okay. 10 minutes is fine for me. Thank you. So now you see that I made a connection with burgers. Burgers is a PD. And I told you that behind burgers, you have the characteristics. And if I was clear enough, then what I wanted to emphasize is that this system, this Fokker-Planck equation and this backward equation is a system of characteristics of some PD, exactly as in burgers. But in burgers, this is pretty easy because this is in finite dimension. Now what I'm saying is that this system of two PDs, this is a system of characteristics in infinite dimension. And the forward equation, so the state equation, mu t, takes values in the space of probability measures. It says that behind there should be a PD on the space of probability measures. And this is really the very fascinating subject. And I think that this is one of the reasons why also this subject has become popular, is that you have plenty of people coming from different areas studying this kind of equation. So this is what we call the master equation. So the master equation is a kind of Eulerian description of a mean field gain. So instead of having a Lagrangian description in terms of characteristics, we now have a description in terms, an Euler description of the problem. So assume that I have uniqueness. Assume that I have uniqueness, which is exactly possible under the previous condition. So what you can do is to say, if I have an initial time, an initial state for the given player, an initial state for the population, I can assign a value to the gain. And the value is what this player, starting from t0, x0, is going to pay when the population starts from u0. So you solve the equilibrium starting from u0 at this time, and then you have chosen the environment, and given this environment, you see what is your best cost. This is this little u. So this is the value of the gain. This is what you have to pay at the equilibrium. And now you say, what is the evolution of this quantity? And I should have a PD for this quantity. This is exactly the derivation of this, is to say, this is a classical argument in stochastic control. You try to prove that there is a dynamic programming principle, which is to say here that if you start from this state and you let a little piece of time evolve, so you run your system by epsilon, so you will receive this additional cost, and then this will be your new state, and you will restart from this new time, this new state, and this new state of the population. And now you say epsilon has to be small. I make an expansion of this, and then I should get a PD by saying, or by identifying the two sides of this equality. So this is the usual verification argument in stochastic control theory, for those of you who know that. Anyway, what I claim is that I should have a PD for that. The difficulty is that I just need to define what is a derivative with respect to a measure. There are several ways to do that. Let me do this quite simply. So if you take a function that is defined on the space of probability measure, here this is the space of probability measure, what you do is that you define a derivative delta v over delta m. You just say that you make convex perturbation on the space of probability measure, and you see that you make an infinitesimal convex perturbation, and you want to represent the derivative of the first order term as the action of mu prime minus mu along the derivative. So you see that the derivative has to be a function of little x, so the gradient is infinite dimensional. This is what it means. And so this is a derivative with respect to the direction of the measure. For those of you who know transport theory and the Wasserstein derivative and so on, the connection between this derivative delta v over delta m and the Wasserstein derivative is that the Wasserstein derivative is the derivative in space with respect to this new variable in the direction v. This is what people call the Wasserstein derivative in transport theory. Anyway, this is an object that is really useful to get the PD that is associated to your main field gain. And this is a PD that you get at the end of the day for your system. I know this is complicated. I don't want to explain to you exactly all these terms, but this is just to say this is now what people are trying to understand. This is the PD that you have behind your characteristics, whether there is a classical solution. And this is something that we can prove. We know that there is a classical solution to this PD under the monotonicity condition that I gave you if the coefficients are smooth. So this was a part of the lectures by Lyons, and then we did a book in which we explained that there was a classical solution. And also I have results with one of your colleagues from the Imperial Dan Christian by probabilistic arguments. We studied also this PD under monotonicity and smoothness of the coefficients. Part of the research now is to try to solve this equation with non-smooth assumptions and possibly outside monotonicity, which is a much more challenging equation. Okay, few things that I want to say back to your question. So what about connection with optimization? Exactly as you said, I could think of a case when my coefficients little f and little g, which is exactly the running cost and the terminal cost that I have to pay in my problem, they derive from a potential. So it looks a bit complicated for you, but this is exactly connected to your question when you thought about a gradient system. So I assume that little f is itself the derivative of some potential capital F with respect to the measure. So you see that this is a function on the space of probability measure, and I take the derivative in the direction m. Monotonicity for little f is the same as convexity for capital F, which is exactly your remark. And now with this new problem, with this new capital F and capital G, I can associate a new problem, which is an optimization problem. This is slightly different. This is there is a subtlety. I take exactly the same Fokker-Planck equation as before, except that now that the drift, the velocity field, is arbitrary. So I have a motion in the space of probability measure, and I tune the velocity in this motion. And given the state of the population, I want to minimize this cost. This is no longer a game. This is an optimization problem. And in this optimization problem, I use the potential as coefficients. Okay, I want to minimize. And in fact, what you can prove is that the minimizers of this, there are solutions to the mean field games with those coefficients, little f and little g. For those of you who come from PD, it means that I can have a look at the value function of this problem. And in fact, the derivative of the value function to this problem should be a solution to my master equation. So this is just a way to say that there is a connection between those mean field games and some optimization problem on collective states. I guess that some of you know optimal transport theory. Optimal transport theory is exactly an example of a minimization problem on a collective state. You want to say, I'm starting from a probability measure, and I want to reach another probability measure in an optimal way, so with the minimal possible cost. This is a problem of this type, except for the fact that the terminal cost is singular. This is infinite if I don't reach the right terminal state, and this is zero otherwise. Okay. So now I'm almost on time, and this was an example. This was just a picture to show you. This is for some choice of the potentials. I can have a look at the terminal state of the population. And in fact, I realized that for the potential, so here this is a curve. The potential there, this is here. So the the minimizer is here. So it would correspond to minimizing this potential in dimension 1. So this is a specific type of mean field game for which at the end of the day I can prove that I want to minimize the mean of the terminal of the mean of the potential of the mean of the terminal state. And you see that the global minimizer is here minus 0.5, and it corresponds exactly to a 0 of this function in blue. And so this is the correspondence between the fact that this minimizer is a solution of the mean field game, but here you have other solutions, other zeros for this curve. It says that there are other solutions to the mean field game. So this is a bit more difficult picture, but this is an illustration. We can absolutely represent this phenomenon. Okay, what is the state of the art today? And just to finish with further questions. Once you have a classical solution to this big object, the master equation, this is a very powerful object to study the convergence. I told you before, you start from the n-particle system, and you want to prove that indeed it converges towards the solution of the mean field game if this is unique. This is a difficult question, and this was solved by using the master equation. In fact, you expand the master equation along the particle system, and you can prove that it looks like very much to what happens when n is equal to infinity. So this was, or this is a crucial use of this notion of master equation, even though it seems to be a complicated and maybe a completely abstract object. This was very useful. Further prospects, so just to tell you direction now, if you're interested in this topic, there are many more models with what we call a common noise, which means that at the same time, we are randomizing the state of the population. So the state of the population is also random. So there are some common shocks in the evolution of the population. For instance, if you think of electricity, it would mean that your price depends on the winds. If you have some production of electricity by means of winds, or depends on the sunlight. If you have some solar panels and so on. From those of you who like PDE, if you get an additional common noise, you get an additional second order term in the master equation. This is quite fascinating to see what is the impact of this second order term on the solution to the master equation. As I said before, you have now some works in the direction of machine learning. You want to use reinforcement learning to solve those mean field games. And once again, I really insist on these on the works by those people, which is really nice. And the other direction is to say, can we use the tools for mean field theory to study some problems in machine learning and reinforcement learning? And maybe you know those works by Montanari, Bach, Van den Eyden, and this is very much connected. What they did is they had a look at neural networks with many neurons, and at the end of the day, they pass to the limits on the number of neurons. And finally, what you do when you want to solve what the stochastic descent does is that it minimizes, or this is a descent along the potential that is on the space of probability measures. And so this was a mean field description of the behavior of your neural network. Further questions. You can think of non-mean field interactions. So mean field interaction is interaction on the complete graph. Everyone sees everyone. You could assume that you see people on a sparse graph. So for those of you who would like to see, I put these names. Non-symmetric models. This is also a new trend in the field. You have this paper, a very recent paper by Laker and Jackson. And one thing that I find absolutely fascinating, this is exactly the picture that I gave you next, or that I gave you before, sorry. Even though I was really quick in the description of this picture, this is just to say that you have this 1D representation of your potential. The global minimizer is this one, but the representation of the MFG equilibria tells you that there are possibly 3 equilibria. And the question is, why should you select exactly this one? And for sure, you could say, well, I'm coming back to the n-particle system and trying to pass to the limit and showing that I'm selecting this one. Well, this is a very difficult problem in general. We can solve it only in some cases. And just to show you the very last picture, this is this one. This is something that I did with one of my PhD students. just to prove that this is indeed the right thing that you select, we randomize a little bit the system. And so here, this is under randomization, this is the mean state of the population, but the population is now random, so the mean state is random as well. And we initialize the population, the mean around 0. And so after some randomization, we get this mean state. So this is a Gaussian state somehow randomized with respect to 0. And so we run some algorithm to look for what should be the selected solution to the mean field game. So there is some iterative construction. And you see that along the way, how it works, we decrease the intensity of the randomization. So the randomization has to be thought as a kind of exploration of the space of probability measure. Here, this is only the space of means, in fact. And at the same time, so we have this, we decrease the randomization and we look for equilibria. And you see how it works. This is a picture that I like. So you reduce the variance. So you see that you converge at the end of the day to a delta mass, and you move to the left. And so you see that the mean of your distribution is shifting to the left. And when you decrease the intensity of the noise, so here this is a noise that is put on the mean state of the population, you exactly reach this minus 0.5, which is exactly the equilibrium that is predicted by this picture and this one. So I know that this is very difficult for you to capture exactly what is behind this, just to tell you that this is a question, and that is quite open at this time for those of you who want to have some conjectures in this field. When there is no uniqueness and you have this potential structure, can you prove that the right equilibrium that you have to select is exactly the global minimizer that you have for the potential? And this is just a numerical illustration to say that this is a phenomenon that we can observe numerically. Okay, thank you.
So my question, you mentioned relaxing the mean field condition. How concrete are results in that form? These are existence proofs, or analyze certain systems? We have this in our fields, different area, but then all hell breaks loose and we're not able to do anything.
Okay, so here, the works that you are going to find, they are more connected with the optimization problem. So you optimize on the collective state of the population. So this is a bit different from the game for which people are selfish. And so what people do is that they have a look at cost, in which the influence of one individual on the global cost is small. So it might not be the same from one individual to another individual, but globally this remains small. And so you see how you can pass to the limit depending on the size of the smallness. So how small is your dependence on your cost in terms of the number of particles. And so depending on the way you decay, as the number of particles grows up, then you can pass or not to the limit.
But I mean, if I understood correctly, your formalism required very much on the law of large numbers to have the same consistency.
Absolutely, in my model, yes. Absolutely. So absolutely, and indeed, absolutely. What I did is that I used law of large numbers and so on. But now people try to say, okay, I forget for part of the symmetry, and then I'm trying to see exactly. I still have the assumption that the influence of one individual on the whole system is small, but they might not be exactly the same, and I have to quantify how small this has to be to pass in some way to the limits. Maybe. Well, no, this is the idea. Maybe we should have a better at the paper. This is a very recent work. In fact, I heard a talk about it just 2 days ago. But this is exactly what the guy said. So if you want to look on archive, to look for it on archive, this is the name of the two authors, Laker and Jackson.
Abstract question. At the beginning, you had this fixed point.
Yeah.
I don't know. Then you start talking about monotone. One starts thinking about fixed point theory. Monotonicity is very there. Does that work at all, like some kind of functional analytic formulation of that fixed point equation that trying to prove existence? Like this kind of random passive functionality.
So maybe I misunderstood a bit your question. There are two things. The first one is that you want to prove existence. So there is no need of monotonicity and so on. If you just want to prove existence, there is no need of monotone operators. Okay, you can just prove this by compactness. Yeah, but here monotonicity can give more than existence. Once again, I can prove existence just by compactness arguments without any further use of monotonicity. I can do this in these types of problems. Now, indeed, you can guess, or you can have monotonicity in addition to this to get further properties, and in particular to get uniqueness. For sure, the fact here is that compactness is easier because you have the heat equation inside, and it gives a lot of additional properties to your solution, smoothness, and smoothness gives you compactness. And maybe if you want to remove the heat equation, indeed, I agree with you that theory of monotone system will be very useful. And if you really want to go to this direction, which is not this is not something that I am an expert in, maybe there is one name that I should cite. Back to my original slide, this is this guy who is really an expert of application of monotone operators for mean-field game system. And this is indeed a case when you don't have the smoothing properties of the Laplace. So you just have a one-order system without the additional Brownian motion. And then indeed you lose part of the compactness properties. And certainly if this is something that you really want to have a look at, I suggest these references. But once again, for what I said, I can say I can prove existence just by compactness arguments, which are quite easy, in fact, because I have plenty of regularity properties on my system, and then prove next uniqueness of the solution using monotonicity properties. I don't know whether this answers your question, but once again, if you are really interested, I suggest the works of this guy.
Is there something in the chat? No, the chat. No. So in a lot of the applications of work that I've seen with mean field games, the interaction comes through the controls themselves and not the state.
Yeah.
And I'm wondering how much of like the existence and uniqueness results are basically equivalent in that setting, or if there are any complications in.
Well, there are some complications. No, there are some complications. In fact, in the book that Roxana mentioned that we did with René Carmona, we put a special section on this case. And I have to admit that I forgot a little bit the additional conditions that you need. But this is one possibility. And once again, I think that the best for me is to give you some references if you are interested. There is another paper by Cardaliague and de Leal, where they have more or less the same kind of conditions. So this is for solving the game, and possibly with some uniqueness criterion, if I remember well. And then there is another class of more recent results about the passage from infinite to n infinity. In this case, when you have the dependence on the law, and then the people are Dylan Posamai and his former student Mao Jete. And so I completely agree with you that there are more technical, this is more technical, this is more difficult. I would not be able here to cite exactly what you need. I don't remember exactly, but I can give you some references if you want. So once again, the section that we put in the book, this paper by Leal and Cardaliague, and more recently a series of works by Posamai and his students. But no, this is more difficult for sure. But we know how to do things. This is my answer. And you have some results in this direction.
questions? In the chat box? Okay, then let's thank François.